Here we go. So, we're going to bring all these pieces together and talk about orbital mechanics. Mateus, are you sleeping? I just want to give you the option of, waking up. You don't have to. If you'd rather sleep, you're welcome to watch the video later. I just didn't want you to be totally unaware of what we're doing. So, a mass m is moving from the surface of a planet to a distance r from the planet's center. What is true about the work done? This is just an analysis of the work energy equation. So it all starts from here. Energy initial plus work equals energy final. We've done this already. Assuming that it's not moving at the beginning and it's done moving at the end, the only energy that we are concerned about is what? The potential energy. So negative GMM over R initial plus whatever work is done is equal to negative GMM over R final. That's just going to be work equals negative GMM over big R, because we're told that work final is big R, minus negative GM little m over little r. And negative means we're adding. So then the work done to move that thing is just given by D. Relatively easy, definitely straightforward, something we saw already like half an hour. The new addition to this, to escape from a planet's gravity, means in theory to travel an infinite distance from the planet. Practically speaking, you don't have to go an infinite distance to escape the effective gravitational pull. Practically, it means to travel far enough away from the planet that the pull of gravity has become very small to barely escape. So there's some verbiage here. To barely escape means to escape from a planet with no kinetic energy left over. You have escaped to as far as you're going to escape to, and now you have stopped. That is the barely escaping. Escaping does not imply kinetic energy equals 0. Barely escaping implies kinetic energy is 0 at the end of the problem. So escape PE equals 0. KE not equal to 0. At that point, KE is going to remain constant like we discussed before. To barely escape, PE is going to equal 0, and KE is also going to equal 0. The number 9 on the previous question, we had to assume that the kinetic energy final was 0. But now we've got language to deal with that. So depending on the question and the language in the question, you're going to have to end up with, you choose which one of these paths you're going to take. Flip the page. So if you got an example that looks like this, a 12,000 kilogram rocket blasting off from Earth barely escapes the Earth's gravitation, or Earth's gravity rather, with no additional engine use. That would be a heck of a ride. You'd probably die. But the rocket might survive. Why? Because we're told that the rocket blasts off from Earth and barely escapes the Earth's gravity. Practically what that means is this. Massive explosion at the beginning, providing you with all of the energy you need to escape the Earth's gravitational pull. Means the amount of work, that initial, that we're ignoring for the sake of this, we're saying, boom, this thing happens, you open your eyes, there's already some initial velocity. The amount of work to do that is fairly substantial. We could figure out what that is relatively easily, but... No, for the sake of this question, we're assuming all the fuel gets used up in the initial blast. Yeah, the acceleration would push the seat through you, possibly like liquefying your bones. You'll see what the initial velocity has to be for this to be possible. Okay? How fast is the rocket moving at launch? So, there's some assumptions here. No additional engine use implies what? No work. All of the work gets done at that pink instant. Then you open your eyes, the rocket's moving. There is some VI at this point. That is what we're looking for. Barely escapes from Earth's gravity implies what two things are true? PE equals KE equals 0. Yes. So we can use the work energy theorem to figure out how fast that rocket's got to be moving. We're also ignoring the resistance due to our atmosphere, which is substantial. So if you're actually going into rocket physics, life's going to get more difficult for you. But assuming Earth has no atmosphere, dealing just with the gravity, here's how this is going to break down. I'll make a note of that. Assuming no atmosphere. How that happened, I don't know. Things got rough on Earth. So, if that's true, this is a work energy style of question. Energy initial plus work equals energy final. At the beginning, how much energy do we have? What kinds of energy do we have? Let's do it that way. We've got kinetic. That's what we're looking for. And we've said PE equals 0 at infinity. So we have to have potential energy to start. Plus PE, that's 0, and energy final is 0. Because we're barely escaping, means potential energy is 0 because we're out at infinity, and kinetic energy equals 0. So we've got half mv squared. Kinetic energy expression is just what it is. Nothing's changed there. Plus negative gmm over r equals 0. So let's solve it. Half mv initial squared equals gmm over r. Our little masses are going to cancel. I can multiply by 2 and square root. So our initial velocity is going to equal the square root of 2g big M over r. And that r is the initial radius of our planet, in this case Earth. So now I can just run those values. 2 times 6.67 times 10 to the negative 11. The mass of our planet, 5.98 times 10 to the 24. Over the radius of our planet, 6,380,000. How fast does the rocket have to be going at launch? Not kilometers. Okay. Convert that into kilometers per hour for us. We'll multiply by 3.6.
40,255 kilometers per hour.
Okay, just to give you guys some perspective on that. No. Hold on here. Okay, hands up if you've watched any of the SpaceX launches that have happened in the last year. Okay, some of you. Okay? I'm trying to figure out when the top speed is reached. So just to put this into perspective for you, the top speed of the Falcon 9. The Falcon 9 is the rocket that SpaceX is using to launch their Dragon manned spacecraft. The fastest that rocket reaches is 39,600 kilometers per hour. So the initial velocity is faster than the maximum speed of the Falcon 9 rocket. That Falcon 9 takes some time to get up to speed. That is the fast. Yes. Well, I mean, is it that fast? I mean, you're in orbit. There's no atmosphere up there. That's relatively easy to do. All your Well, I mean, because it starts at 0 and then launches, right? And it starts slowly. The argument here is that this rocket would have to start, again, I'm assuming a few things, no atmosphere, with a velocity of 40,255.2 kilometers per hour. The speed's not the issue. The issue is the acceleration from 0. That's the problem. As far as we're aware in the question, all of the rocket fuel gets used, has to, because we can't analyze there's a whole bunch of problems with this, right? Like an actual rocket. If you have never had the opportunity to watch a SpaceX launch, they're live streamed on YouTube. Watch a SpaceX. They are very cool. And it gives you some perspective on the staging that happens here. It's a massive rocket, uses up a bunch of fuel, then drops off the back chunk, then uses up a bunch more fuel, then drops off the back chunk. Once the thing's actually in orbit, then the Dragon disconnects, and the Dragon goes off to the International Space Station. So it's a fascinating thing to watch. It takes about, once countdown hits 0, it's about, I'll say about 20 minutes until the thing is finally in orbit on its way to the ISS, because it takes like almost a day for it to reach the space station. So the real good stuff takes about 20 minutes. And it's constantly losing mass, right? Like it's using up fuel and it's dropping off big pieces of the rocket, allowing it to go faster and faster and faster and faster. Our rocket has none of that happening, as far as we're aware. So the problems, like the actual physics behind a real launch, a lot more complicated, but the same concepts do apply. Yeah. Oh, see, that's the beauty of the space. That's the other thing you got to watch about SpaceX. They used to just fall off, land in the ocean. Like, so if you, like when the Apollo program was launching, the Saturn V rocket, that blue poster at the back, next to the door, that is the Saturn V rocket. That's what sent astronauts to the moon. And you can see the different stages on there. Like it's built to show you all the different stages. It was one big tall thing, but you can see there's rocket boosters at the bottom, and then about a third of the way up there's more, and then about the third of the way up again there's another little one. So everything below that is stages that would fall off. They would just fall into the ocean or burn up on re-entry. But now the SpaceX ones, they actually land themselves again, which is pretty cool. Really? Yeah, it's super fascinating. There's a barge that floats out off. Well, yeah, when they fail, it's cool too. But when they actually land, it's pretty wicked. If you have the opportunity to watch a SpaceX launch, definitely do it. It's at least one. It's fascinating. I've watched, I want to say 3 or 4 now, and I saw some of the failed ones. There was a couple times when there was launches back before SpaceX was a thing. They were launching out of. So the space shuttle program no longer existed. So NASA wasn't launching anything in Florida. They were doing all the launches out of Kazakhstan, because when the Soviet Union was a thing, that's where the Russians put their launch site. It was in Baikonur in Kazakhstan. The time difference meant that rocket launches were happening during the middle of our afternoon. So I actually watched a couple with my physics class 3 or 4 years ago. We actually watched rocket launches in class during this unit because it just happened to line up with a Russian launch out of Kazakhstan. It was really cool. Well, the Russian launches are wild. Like, you never know what's going to happen. It was a live feed off of YouTube that we were watching in class. It was cool. Okay, questions about the procedure. You know what? Yeah, I don't mind actually. I'll see if I can find a video. Once we finish the lesson, I'll toss the launch up. You can take a look at how they go. There was one more big example that we're gonna do, because these things don't just blast off to infinity. They blast off into orbit, and they've got some uniform circular motion going on. That's what actually happens. So let's do one of those. So this stationary 12,500 kilogram rocket blasts off from Earth. It enters a circular orbit 25,500 kilometers from the center of the planet. Ultimately what we want to find is the work required to put the thing into orbit. That is how this thing is going to be phrased on a test or exam. Because that's ultimately what we want to know. And jumping straight to here, this tells you how we have to proceed. We have to deal with work energy. But we're going to combine all the pieces that we've dealt with so far in this chapter and the previous one on energy and momentum. Let's go. We're going to need a fair bit of space here, so I'm going to start up here top left. To identify the work required to put this thing in orbit, we're dealing with this. Energy initial plus work equals energy final. What kind of energy is present and where is it located? Oh, sorry, I shouldn't say that. What kind of energy is present and when? I'll say it that way. Sorry? We're told the thing starts at rest. So this is a little bit different. This one now, instead of opening your eyes after the explosions happened and there's a ton of energy present, you're now watching this thing launch. It's not moving. Engines ignite. What we want to find out is how much work is required by those engines to put this thing into a stable circular orbit. Nathan.
We're going in between two times, so usually potential beginning, potential.
You're correct about the beginning. There's potential energy at the beginning. There's a bunch of work done to put this thing into a stable, uniform circular orbit. So a uniform circular orbit requires what? Requires a constant velocity. So what kind of energy is present at the end? Kinetic. And this thing's not, it's in orbit, so it's not out of the gravitational pull. If it was, it's not orbiting in a circle because there's no inward force. But there is an inward force. The inward force is gravity. So what kind of energy must also be present at the end? Also have to have potential energy at the end. So that's the analysis of this whole thing. So we've got work is going to equal the kinetic energy, I'm just going to solve for work now, because why not, plus potential energy final minus potential energy initial. We've got expressions for all of these things. Work is going to equal, our expression for KE is what? 1/2 mv final squared. A couple different colors for this. Plus potential energy final is given to us by what? GMM over, we'll call this R final, plus negative GMM.
Negative.
Sorry, minus. Oh, right. That's why I had it right that way. It would have been minus, which is going to become plus in here in a second. So let's write this out one more time. 1/2 mv final squared minus GMM over R final plus, that's why it was plus, GMM over R initial. That's the expression that's going to give us this work. Easy, right? Unfortunately, all we're told is this. The rocket has a mass of 12,500 kilograms. It enters a uniform circular orbit. The radius of that orbit is 25,500 kilometers. That's all we're told. So where do we go from here? Some of these things are really easy to input. Where's the challenge? What's the challenging, slightly more challenging piece? The velocity. The velocity is the problem. We know big G, we know big M, we know little m, we know R final, we know R initial. It's this V piece is where things are going to get a little bit hairy. Why? Sorry, Garissa, I'll keep going. But why? No, why? Not how. Why is there more work to do with this? Nathan. He's phoning a friend. Why is this VF the problem? Where's that V coming from? You would also like to phone a friend? Ashton, where's this VF coming from?
That VF is coming from the kinetic energy formula, but the problem comes because you have two unknowns. Your work is unknown and your...
No, we're looking for work. But yes, it comes from kinetic energy. But AJ, yes, this is the velocity required to keep this object in a circular orbit.
Whatever.
So we have to analyze this VF using uniform circular motion. Thank you, AJ.
Just about.
Okay, so let's find VF. We have to start like we always do. FNC equals MAC, and we know that AC equals V squared over R. I am jumping straight. You cannot use this. V equals 2 pi R over T. It would be nice if we could. We don't have the length of time of the orbit. That's the problem. So we can't use this one. So we have to use a combination of this one and F net equals MA. You cool with that? Okay. So that's why I've jumped straight to here. So the force inwards on the rocket is given to us by Fg. So we're going to have GMM over R squared equals MV squared over R. Things are going to simplify here nicely, giving us that V, the expression we found before, is equal to the square root of G big M over little r. And just for fun, rather than inserting values in at this point, I'm just going to shove this expression back into this guy here. Because I have v squared and I have a square root. So those are going to cancel out. So this is just going to give us this expression here. 1/2 times the mass. I'm going to write it in here just so we can see what's going on here, but it's the square root of gm over r all squared minus gmm over our final. Oh, and this is our final. That's the speed in orbit. Plus gmm over our initial. Some fun stuff's going to happen here. The squared and the square root are going to cancel out. So we're going to get that this expression here, work is going to equal, look what happens on the inside here. It's going to be 1/2 G big M little m over our final minus G big M little m over our final plus GMM over our initial. That green guy right there looks an awful lot like what? Looks an awful lot like the blue guy. So we had an expression for kinetic energy that now looks an awful lot like the expression for the potential energy, which is a fun little result. So we can plug some values in here and away we go. So I'm going to go down here. This thing's going to get wild. Okay, so we're going to get 6.67 times 10 to the negative 11. The mass of the Earth, 5.98 times 10 to the 24. The mass of the rocket, 12500 over 2 times radius final, which is 25 million meters.
Could the driver of a silver Audi license plate FL563A please go to the parking lot? That's the driver of a silver Audi FL563A. Please see Mr. Studio in the parking lot.
I ran out of space again. That's okay. Plus negative 11 times 5.98 times 10 to the 24 times 12,500 over 6,380,000, because that's the initial radius of our object. To make your life easier, you can, each one of these expressions can be dealt with in your calculator on its own. You can insert those values. Some way you're going to have to find a comfortable way to calculate that. What is the work? Grab your calculators. See what you get. Yeah, actually, if when you get a value, let me know.
6.84 times 10 to the 11.
Does anyone get the same thing? Hands up if you got the same value. Is this your version of committing to Nathan? Does this mean you got the same value?
No.
Oh.
I was still writing it when you guys were
Okay.
halfway through calculating it.
Someone's got to verify that value. 6.84 times 10 to the 11 joules.
Oh.
Okay, anyone able to verify this thing yet? Shannon, you got the same thing? Zach got the same thing? Okay, cool. Guys, flip the page. We have already done this portion here. Example 4 says to use the expression for orbit speed to prove that in the circular orbit the kinetic energy is half the magnitude of the potential energy, the total orbit energy is half the PE, and the total orbit energy is the opposite of the kinetic energy. We've already done that. That's effectively what we got here. Total orbit energy is just those two pieces there, which would have been these two pieces here. So I'm not going to do that example in full. We've already seen how those results can pop out, especially at this portion right here. So flip the page again. This one's just an exercise in analyzing the wording of the question to be able to identify energy that's present at the beginning versus at the end, depending on how this thing is phrased. So, because that's the hardest part here, is being able to identify that. So, let's just go through some of these real quick here, make sure we're good, and then you guys can work on the rest of this. And we'll do the last lesson tomorrow. Yeah, we'll do the last lesson tomorrow. I'll give you the reviews tomorrow as well. So, all of these start from this assumption that we're assuming the work energy theorem is true, which it is. By definition, work is the change in energy. How does it look, though, for each of these situations? A rocket at rest on the surface of Earth blasts off and rises to a maximum altitude height of h. So the maximum radius is r. What is our work energy theorem going to look like for this situation? There's going to be potential energy initial plus work equals potential energy final. Why is there no kinetic energy anywhere, Blake? The implication of a maximum height implies, just like a projectile, at the maximum height, the upwards or the outwards velocity is 0. In this case, this thing's only going, there's no additional components one way or the other. So if it's just blasting straight out and stopping at some maximum height, there's no kinetic energy at the end. We're told it starts at rest. There's no kinetic energy at the beginning. Cool? Next one. Someone else. B. A rocket moving at speed v at liftoff, i.e. near the Earth's surface, rises to a height h with no engine use. It's moving at speed v at liftoff. So kinetic energy initial plus potential energy initial. No engine use implies that work equals 0 equals potential energy final, because we were told that there's some maximum height. Cool, next one. What's going on with this guy? Yeah, Nathan. KE final, PE final equals 0. Okay, so what's the entire equation? Well, I'll just say plus work equals 0. Yeah. Okay. Yeah, then you can move it around from there. Okay, someone else, D. Okay, Joseph. You say that there's kinetic energy initial. Okay. Because there is a moving at speed v at liftoff. Okay, keep going. Yeah, there's always potential energy initial in these launch questions.
It says, fairly steep with no engine use. So there's not going to be no work, and then it's going to equal 0 because fairly steep. Yes.
KE final equals PE final equals 0 without at infinity at rest. Okay, keep going. Someone else, E. If any questions about any of the reasoning of your classmates, please do ask. So far, they've all been correct. Someone else, E.
Yeah.
Okay, sorry, Chris. Abigail. So it starts at rest, so there's no kinetic energy to start. It blasts off, so there's implication that work is done. Enters a circular orbit, which tells you that there has to be kinetic energy at the end due to the circular motion. That should be of radius r, not or radius r. So PE final. Cool. Love it. Someone else. F. You already did one, Nathan. Anybody. Here's Hill. You think you got it? No, the crystal's on it. I'll wait till someone else does it. Here's Hill. You got it? Okay, let's do it. Why?
Because we tried.
Love it. Next. Okay. Well, where's the work? Love it. Work equals 0 because there's no further energy is. Now keep going. Why is there kinetic energy final? Because it has a circular orbit of radius r, which tells us that there's also potential energy at the end. Cool. Love it. Perfect. Love it. And G is similar to F. The only difference between F and G is what? It starts in orbit and falls back to Earth. So if it starts in orbit and falls back to Earth, what has to be present initially? There has to be kinetic energy to start because it was in it is moving at speed v at a distance r, which tells us that there's some potential energy initially. It's falling. So falling implies that work equals 0 unless we're told what? Unless we're told that there's this much energy lost due to heat. Unless heat is mentioned. In this case, it's not. So that's going to equal what? How is it going to end? Sorry, there was two different things said there. This and when we think about it, when we thought about falling to the Earth's surface, it's just the instant prior to impact. Abigail, go again. There would definitely be kinetic energy. No, it's like it would be the impact velocity is what you'd have here. And then because we're using this is where the following is different. We are using universal gravitation for this because the object started in orbit. So what also has to be present at the end? There still has to be potential energy at the end. This is the one that trips people up because for falling objects, we used to say MGH is 0. But now because we're using universal gravitation, because this object started in orbit, it has to have potential energy at the end. Because we're taking 0 to be out at infinity, the object's not at infinity, it's at the Earth's surface. And the potential energy formula includes that distance between the center of the Earth and the Earth's surface. So this is the term that messes people up. That's it. That's all I got for you. Flip the page. Let's see what you can do with this. You're going to do 1 to 4. Oh, hold on. Yes, there are 2 6s.
We should cancel each other out. Yeah. 6 over 6 is just 1. So just 1. Just 1. Number 1. Oh, brilliant.
But it's not 6 over 6. It's 6 plus 6, which is 12.
Oh. But it's on top of 6. On top of it.
Okay, just to make this really easy so there's no confusion about the numbers 6.
What? We're going to do them both? Oh, God. This is cool. So it's really 1 to 8, but not.
No, it's 1 to 7.
Yeah, but that's 8.
That's 8 questions. No, it's 9 questions.
Oh,
1, 2, 3, 4, 5, 6, 7.
No, that's 8.
Oh, no, it's 8 questions. You're right. There's no question 0. But that's what I'm assigning. There you go. All the questions between 1 and 7 is what I want you to play with here. While you're working on this, I will toss the space up. I have not forgotten. I will toss the SpaceX launch up because I think they're worth watching. As soon as I can find the one I'm looking for.